Have you ever gazed up at the night sky and seen a single lonely point of light? That star might not be as solitary as it appears. In fact, many stars that look like one to our eyes are actually two, three, even more, locked in a complex gravitational dance. Imagine three massive fiery suns, each pulling on the others, swirling through the cosmos in a waltz that can last for billions of years. This isn't science fiction. This is the reality of a triple star system. These celestial trios are some of the most fascinating and dynamic arrangements in the universe, showcasing the raw and sometimes unpredictable power of gravity in its purest form. A triple star system is exactly what it sounds like. It's a system where three stars are gravitationally bound together. Each star feels the gravitational pull of the other two. This constant tug-of-war dictates their movement. Their orbits aren't always the simple, neat ellipses we see with planets around a single sun. Instead, they can be wonderfully complex, a cosmic puzzle that astronomers have been piecing together for centuries. The most common and stable type of triple star system is what astronomers call a hierarchical triple. It's the universe's secret to keeping a three-body family together without it all falling apart. Think of it like a family structure. You have a very close inner pair of stars, orbiting each other like inseparable siblings. Then, much farther away, there's a third star, orbiting this central duo like a distant guardian. This arrangement creates a clear chain of command, or hierarchy, in the gravitational pulls, which is the key to its long-term stability and survival over billions of years. The physics behind this stability is surprisingly straightforward. The two stars in the inner binary are very close to each other, meaning their mutual gravitational pull is incredibly strong. To avoid crashing into each other, they have to orbit at very high speeds. This tight, fast orbit makes the inner pair act almost like a single, more massive object from the perspective of the distant third star. That third star, being so far away, has a much weaker gravitational influence on the inner pair. Its pull isn't strong enough to disrupt their tight embrace, so it simply ambles along on its own vast, slow orbit around their combined center of mass. Not all triple star systems are as orderly as the hierarchical model. When the three stars have comparable masses and are all at similar distances from one another, the system can become dynamically unstable. This is where the real chaos begins. In this scenario, there is no clear hierarchy of gravitational influence. Each star pulls on the other two with significant force. Their orbits become wildly unpredictable. It's less like a graceful waltz and more like a cosmic mosh pit. The future path of any given star is nearly impossible to calculate over long periods. This chaotic behavior stems from what is known in physics as the three-body problem. We can perfectly solve the equations of motion for two bodies, like the Earth and the Sun. Add a third body and the mathematics becomes notoriously complex, often unsolvable with a simple formula. Tiny, insignificant changes in a star's initial position or velocity can lead to drastically different outcomes. One star might get a gravitational slingshot from a close pass with another. That slingshot can send it on a completely new trajectory, unforeseeable moments before. These fascinating triple star systems aren't just theoretical concepts, they are sprinkled throughout our night sky. One of the most famous examples of a stable hierarchical system is Polaris, the North Star. For centuries, sailors used Polaris as a fixed navigational point. What they didn't know is that Polaris is not one star, but three. Polaris A. The main star, Polaris A, is a massive supergiant. Polaris AB orbiting it very closely is a smaller companion, Polaris AB, which was only confirmed by the Hubble Space Telescope because it is so close. Polaris B, much farther away, in a wide 24,000-year orbit, is the third star, Polaris B. This is a perfect textbook example of a hierarchical system. Another well-known triple system, one that you can even see with a good backyard telescope, is Alpha Centauri. Located just over 4 light-years away, it's our closest stellar neighbor, Alpha Centauri, A Alpha Centauri B. This system consists of a tight binary pair, Alpha Centauri A and Alpha Centauri B, which orbit each other every 80 years. Diagram. And the system has a third member, Proxima Centauri. These two stars are quite similar to our own sun. Proxima Centauri. This small dim red dwarf is the closest star to our solar system and orbits the main AB pair from a tremendous distance, about 13,000 times the distance from the Earth to the Sun. Its orbit is so vast that it takes over 500,000 years to complete a single lap. Venturing into more exotic territory, we find systems that hint at a more dynamic past. The star system GW Orionis, located about 1,300 light-years away, has perplexed astronomers. It features a hierarchical triple, with an inner binary and a distant tertiary star. What makes it so strange is the vast protoplanetary disk of dust and gas surrounding the stars. The disk is not flat. It has been warped and torn into 3 distinct misaligned rings. First ring, second ring, third ring. It's the first direct evidence that the gravitational tug-of-war in a triple star system can have a profound and violent effect on the very material from which planets are born, literally ripping a solar system apart. These real-world examples show us the diversity of triple star systems. From the calm, predictable arrangement of Polaris to the system-shaping power seen in GW Orionis, each one provides a natural laboratory for testing our understanding of gravity. By studying the light motion and structure of these distant trios, we can piece together their histories and predict their futures. They are a constant reminder that the universe is often more complex and more interconnected than it first appears, with hidden companions and unseen dances playing out all across the cosmos. And that's the long and short of it. The intricate dance of a triple star system is governed by a few fundamental laws of physics, with gravity taking center stage. Gravity is the invisible choreographer, the force that dictates every move. Its strength depends on 2 simple things: mass and distance. A more massive star exerts a stronger gravitational pull the closer 2 stars are, the more intensely they tug on each other. This is the foundation of everything. The constant interplay of these gravitational forces between all 3 stars creates their complex, interwoven orbits and drives the entire system's evolution. Beyond gravity, 2 other crucial concepts are at play: energy and angular momentum. Think of energy as the system's total capacity for motion. This energy is divided between kinetic energy, the energy of movement, potential energy, the energy stored in the gravitational field. Because chaotic triple star systems are inherently unstable, they are destined to change. They are temporary arrangements on a cosmic timescale, and they must eventually resolve their internal gravitational conflict. The most common outcome of this chaotic dance is ejection. In a series of close and powerful gravitational encounters, one of the 3 stars can get slingshotted with such force that it gains enough speed to escape the gravitational pull of the other 2 entirely. This runaway star is then flung into interstellar space, destined to wander the galaxy alone for the rest of its existence. What's left behind after an ejection is a stable binary star system, the 2 remaining stars, having given up a significant amount of energy and angular momentum to the ejected 3rd star, settle into a much calmer and more predictable orbit around each other. In a way, the system has sacrificed one of its members to achieve long-term stability. This process of dynamical decay is thought to be a very common way that binary stars are formed in the universe. Many of the binary systems we see today may have started their lives as part of an unstable triple or even a larger star cluster. While most triple star systems fall into the categories of stable hierarchies, unstable chaotic messes, there exists a third, exceptionally rare possibility. In 1993, a physicist named Chris Moore discovered a surprising and beautiful solution to the 3-body problem, at least in theory. He found that 3 stars of equal mass, starting from very specific positions and velocities, could chase each other along a single, repeating figure-8-shaped path. This is not a hierarchical system. It's a co-orbital dance. All 3 stars share the same looping track, like race cars on a cosmic speedway. In this delicate configuration, each star follows the exact same path, one after the other, in a perpetual cycle. The gravitational forces between the 3 bodies are perfectly balanced at every moment to maintain this intricate choreography. Imagine one star at the top of the 8, another at the bottom, and the 3rd crossing the midpoint. As they move, they seamlessly trade places, with their mutual gravitational pulls guiding them precisely along the figure-8 curve. The existence of a triple star system raises a tantalizing question. Could planets exist there, and what would life be like under three suns? The answer is complex and depends heavily on the system's stability. In a stable hierarchical system, planets can indeed exist. A planet could have a stable orbit if it is very close to one of the stars, essentially treating the other two distant stars as faint, wandering points of light in its sky. This is known as a circumstellar orbit. In this scenario, the planet's climate would be dominated by its primary star, much like Earth's is by our Sun. Alternatively, a planet could exist in a circumbinary orbit, circling the tight inner pair of stars from a great distance. From the surface of such a world, one would see two suns in the sky, orbiting each other like a fiery dumbbell. The distant third star would appear as a very bright, slow-moving star that would travel across the constellations over many years. An even grander possibility is a circumtriple orbit, where a planet circles all three stars from a vast distance. But such an orbit would need to be incredibly far out to remain stable, likely leaving the planet a frozen, desolate world. Life on a planet in a chaotic triple system, however, would be a nightmare. The unpredictable orbits of the stars would lead to wild and extreme variations in the amount of light and heat the planet receives. It could experience long periods of freezing darkness, followed by scorching phases with multiple suns blazing in the sky. Worse, the shifting gravitational pulls could easily disrupt the planet's orbit. In the grand theater of the cosmos, the story of a triple star system is a compelling drama in 3 acts. We've seen that these systems are not a chaotic free-for-all, but rather a fascinating interplay between order and instability. The first and most crucial point to remember is what they are. 3 stars bound together by their mutual gravity, their movements dictated by an endless, intricate dance. This dance can take on different forms, but it is always, at its heart, a story written by the fundamental force of gravity. Secondly, we've learned how these systems behave. The vast majority find stability in a hierarchical arrangement with a close binary pair orbited by a distant third companion. This structure separates the gravitational interactions, allowing the system to persist peacefully for billions of years. In contrast, when the stars are too close in mass and distance, they enter a chaotic phase. A temporary, unstable dance where their futures are unpredictable and dramatic change is inevitable.